Okay. Hello, hi everyone. Good morning, good afternoon, good evening, wherever you are. It's a pleasure to host you this week again with another geoscientific and geoenergetic talk. Today, Sebastian couldn't make it. We have the pleasure to co-host you with Kamal Singh from Heriot-Watt University. And I'm at work. I'm in my office, so we are getting back little by little back in office. We were just speaking with our speaker as well that things are getting better everywhere. We have today the pleasure, honor of hosting our colleague, Professor Lauren Beckingham. Lauren is assistant professor in the Department of Civil and Environmental Engineering at Auburn University in Alabama. She holds PhD and MA, Master of Art in Civil and Environmental Engineering from Princeton University, and a BS Bachelor of Science in Environmental Engineering from Michigan Technological University. Prior to joining Auburn, she was a geochemical postdoctoral fellow at Lawrence Berkeley National Lab in California. Her expertise and interests are in understanding water-rock interactions in environmental systems, particularly in subsurface energy systems, including geological carbon monoxide, CO2, carbon dioxide, CO2 sequestration, and compressed energy storage, the two very, very hot topics these days, quite impactful for energy storage and also climate actions on CO2 sequestration. Her lab is currently supported by NSF, National Science Foundation, including a 2019 Career Award, and also funded by American Chemical Society and Department of Energy, among others. It's our true pleasure and honor to host you, Lauren, today with us. Thank you very much for graciously accepting our invitation. Despite the start of academic year, we could imagine how busy you are with so many emails from students and colleagues. To the audience, please note Lauren's lecture would last for about half an hour, about 30 minutes, followed by questions. Like always, please do type your questions in the chat box, and Kamal will go through them during the discussion session after the talk. Please do not wait until the end until you post your questions. Whenever you feel appropriate, please do type them. Your question makes other people also encouraged to post questions. We can't give awards. We are not in-person meeting, but we would offer chocolate boxes to those who would ask questions as well. But it's hard to do that online chocolate box, but that's how it is. So thank you all once again, especially our distinguished speaker, Lauren. The stage is all yours. We are very much looking forward to hearing your presentation.
Thank you so much. Can you see the slide?
Yes, okay? Perfectly.
Yeah, perfect. Thank you so much for the invitation. It's a pleasure to be here today. And I'm looking forward to sharing with you some of the things that we've learned about geochemistry in subsurface energy systems. So we're all probably aware that atmospheric emissions of CO2 continue to increase. And if we take a look at where emissions are coming from, we can see they're predominantly from means of energy production. If we then look at the CO2 intensity of different ways of energy production, here you can see the really CO2 intensive processes at the top of the screen and the less CO2 intensive means of energy production at the bottom of the screen. So if we want to try to reduce our atmospheric emissions of CO2, we need to think about how we can shift our energy profile from relying so heavily on those that are really CO2 intensive to means of energy production that are less CO2 intensive. And so one way we can do that is by amending traditional coal-fired power plants with carbon capture and storage. So we can capture CO2 at the power plants and inject it into deep geologic formations like saline aquifers, where it will remain indefinitely. We can also increase our reliance on renewable energy, but this requires a means of energy storage. And the subsurface is really a promising place for long-term and large capacity energy storage. So thinking about geochemistry in these systems, in carbon storage in a saline aquifer, the CO2 is going to dissolve into formation brine and create conditions favorable for dissolution of primary minerals. This can then, in turn, result in secondary mineral precipitation of carbonate minerals that will permanently trap the injected CO2. This is referred to as mineral trapping and is a really secure form of CO2 trapping. However, we don't really have a great understanding of the rate and extent of mineral trapping. And so I've replaced this time on this plot with just an arrow, because this is an area we need to improve our understanding. We also don't understand how those reactions will impact formation properties. For example, the evolution of porosity and permeability. In terms of energy storage systems, when you have excess energy from renewable systems, you can use that to inject a gas into a geologic formation. And then when you need to recover that energy, you can extract that working gas from the storage formation. Currently we're doing this a lot in salt caverns, but saline or porous formations, saline aquifers are promising potential means of energy storage that are ubiquitous. So in these systems, you're often going to start by injecting a cushion gas, which serves to raise the formation pressure, as well as push the brine away from the injection well. And then you're going to start injecting your working gas, which is the one you're going to be cycling through for energy storage and extraction. And so you end up with these really different kinds of zones in the system where the cushion gas may or may not be the same formation or the same composition as the working gas. So if thinking about geochemistry in these systems, near the injection well, you might start having salt precipitation, and then further out into the region where the cushion gas is mixing with the brine, you might have some additional kinds of dissolution and precipitation reactions. Like the CO2 storage system, we also have complications of multi-phase flow. There might be some other things going on if we have variations in gas composition, and then we have this unique cyclic flow that might impact the geochemical reactions in a slightly different manner. So today we're going to briefly talk about a few different things. First, about reactive surface area, and then porosity permeability evolution, and then briefly about geochemistry and energy storage systems. So why do we care about reactive surface area? Well, the way that we typically simulate mineral reaction rates is to use a rate law from transition state theory. So here, the dissolution rate is proportional to some rate constant, some thermodynamic component, and the reactive surface area. Well, we have a pretty good understanding of the thermodynamic component. We really have a poor understanding of reactive surface area. And if you look at reactive surface area values that have been used in previous geologic CO2 simulations, you can see that they span several orders of magnitude. And this is a problem because they're directly proportional to our simulated mineral reaction rates. So why are we getting this really large range of values? Well, we don't really have a good way to approximate surface area or understanding of how we should approximate it. The simplest approach is to use a geometric surface area where you just assume all minerals are perfectly smooth spheres of the same diameter. The problem with this, though, is that we know that clay minerals are inherently different than other minerals and have a much larger surface area. We can account for this by using two surface areas, one for clay minerals and one for everything else. But we also know that mineral surfaces are not perfectly smooth and have some amount of surface roughness. We can account for this by using a roughness factor. This is typically a factor of 10. This rough surface area or specific surface area, you can also get in the laboratory from doing a BET measurement. Now, we've also seen evidence that potentially only some sites on the surface are actually going to be reactive. We can account for this by applying a scaling factor. This is somewhere between 1 to 3 orders of magnitude, where the modeler just picks the value that they want to use. There's really little guidance on what value you should be using. And sometimes the scaling factor is applied directly to the geometric surface area. And so now the problem is we end up with really wide ranges of potential surface area values that we can use. And all of these different approaches have been used in the reactive transport simulations. But none of these account for the fact that not necessarily all mineral surfaces are going to be accessible for reaction, or for the fact that the surface areas might actually evolve during reaction. In recent collaborative work, we used a multi-scale imaging approach to actually quantify the surfaces of minerals that would be accessible for reaction. So we combined 2D SEM imaging with high-resolution Fib SEM imaging to look at the nanopore structure of clays. We can account for connectivity in 3 dimensions through CT imaging and actually quantify mineral-specific accessible surface areas. We validated this with core flood experiments and then carried out continuum scale reactive transport simulations of the experiments with crunch flow. When our simulations used or assumed that all mineral surfaces were accessible, we really overestimated the extent of reaction happening in experiments. But when we used our image obtained accessible surface area, we found we were able to successfully capture the reaction rates from the core flood experiment. So what we wanted to understand then is a little bit more about the imaging process. In particular, what resolution should we be collecting the images at? Is that going to have an impact on the values that we are calculating for the simulation, including the volume fractions and accessible surface area? And then if we do have variations, how does that impact the simulation results? And so this was work that was done by my PhD student, Fanchi. Here we used a sample from the Biloxi Formation, which is a potential pilot CO2 injection plant in Kemper County, Mississippi. We used SEM imaging to determine the distribution of minerals within a thin section. And so here, each color corresponds to a different mineral phase. This sample is predominantly quartz, but does have some reactive calcite shown in red, as well as some clay, smectite illite in yellow, as well as feldspar minerals. Looking at mineral abundances, or the volume fractions that you get by just counting the pixels, we saw that they agreed relatively well for, or repeated this for 5 different resolutions from 0.3 microns to 5.7 microns, and then quantified the volume fractions and found really little variation among the different image resolutions. Now, if you zoom in here at the bottom, looking at some of the small scale features, though, and thinking about surface area and accessibility, we did see some variation in the accessibility of these different mineral phases. So here's the accessibilities with different image resolutions, where we see an increase in quartz accessibility with decreasing resolution, and a decrease in smectite illite, or our clay mineral here, with decreasing resolution. So as you decrease the image resolution, it's no surprise that you have a hard time capturing the small scale features. To account for connectivity in 3 dimensions, we used X-ray CT imaging, where we extracted cuboids matching with the same total slice surface area as our 2D image, and then quantified the accessible surface area and from a series of cuboids and multiplied by accessibility. And so looking at the variations in accessible surface area, we see an increase in quartz accessible surface area with decreasing resolution, and reductions in potassium, feldspar, and calcite surface areas. But you'll notice these variations are relatively small, just within 1 order of magnitude. And so does this have any impact then on the results of reactive transport simulations if you use this data to construct your model? So here we carried out crunch flow simulations at the continuum scale, mimicking the conditions at the site. We tracked the evolution of mineral volume fractions, surface area, and porosity. And we considered 2 time scales, one of a short time scale, about 2 weeks, which is pertinent for like a laboratory experiment, and then a long time scale of 20 years, which is more pertinent for the field scale system. We looked at a variety of different surface areas. So the surface areas from the highest and lowest resolution images, but then also surface areas from traditional approximations, including 2 geometric surface areas, which are about 1 to 2 orders of magnitude higher than the accessible surface areas, and then 2 specific surface areas from the BET measurement in the lab, which are even higher than the geometric surface areas. We're not going to go through all of the results, but just I'm going to show you some of the highlights here. So this is the results from the imaging-based simulations. What we see over short time scales is we have rapid initial calcite dissolution. We also have siderite dissolution. Simulations that use the surface areas from the high resolution images are the solid lines, and the dotted lines are using the surface areas from the low resolution images. And you can see here over this short time scale, there's really little difference in the simulation results. If we look at longer time scales, now we start seeing smectite dissolution as well as quartz precipitation, and really little variation between the simulation results. In terms of how porosity is impacted, we see an initial increase in porosity from 25 to 33%. And then over long time scales, porosity starts reducing again to 29 to 31%. So there's some slight variations in the two results, but not very extreme. If we now compare that with the simulation results using the other surface area approximations, we're just going to look at porosity. Here on the short time scale, we see that they agree relatively well with each other, predicting increases in porosity that are pretty similar. But over longer time scales, we can see we have a lot of variation. So some cases you have further enhancements in porosity and then much more drastic reductions in porosity over time. So what happens kind of depends on the minerals that you have and what kind of timescale you're interested in. So for us, the most reactive minerals are the carbonate minerals in this system. We see some large variations in siderite among the surface area values we use in our simulation, but really no variations in the more stable phases. But then over the longer time scales, we're seeing lots of variations in these more stable minerals and really no variations among the most reactive phases. So do we always need to use this imaging approach to figure out accessible surface areas? Well, it maybe just depends on what you're interested in. So if you're thinking about your laboratory experiment or short time scales, it's really important to have a good understanding of the most reactive phases. But if you want to understand much longer time scales, then it's the most important to understand the surface area and accessibility of those more stable mineral phases. So getting these values is very time and resource intensive. So what we want to know is if there's any way we can possibly predict the accessibility of different mineral phases. And so we've looked at a variety of different sandstone samples with varying clay and carbonate content. And we've carried out this analysis. So this is just a selection of some of the data that we've produced for all of these different sandstone samples, and then trying to see if we can come to any conclusions or any observations and relationships between these parameters. And so I'm just going to share with you some of the preliminary observations we have so far. So in terms of mineral accessibility, we have noticed that quartz is often covered with clays or carbonates. And so the accessibility of quartz is often overestimated by the abundance. In terms of the feldspar minerals, we've noticed that they are reflected relatively well, or their accessibility is reflected relatively well by abundance. And then we considered, well, what if we normalize the abundance by the amount of clay in each of the samples? And so here you see quartz, carbonate, and the feldspar minerals. Abundance is normalized by clay content. And you can see that there's some kind of increasing accessibility with this increased normalized abundance. So this there might be some kind of relationship here and dependence on clay content. If we look at the total connected surface area, we can see it generally decreases with the amount of quartz, which is kind of what we expected because quartz is potentially has a smoother surface compared to other minerals. We see that it's not really highly dependent on carbonate content, so you have some initial increase when you have 0 to some small amount of carbonate, but then it's relatively stable. We also looked at variations with clay content. There could be a couple of things, different things happening here, where clays can increase roughness, but may decrease connectivity. I will note that we did account for nanopore connectivity in some of the clay minerals that we have data for via FibSim analysis. In terms of accessible surface area, we see that carbonate accessible surface area increases with abundance. And just for comparison here, these are the BET specific surface areas that we've collected from the literature shown as stars. And we've just kind of highlighted this region to give you an idea of how these accessible surface area values compare with the BET specific surface area values. And then if we plot all of the accessible surface areas versus porosity, again, you can maybe notice in general some kind of decreasing trend in accessible surface area with increasing porosity, but it's not completely clear. So we're still working on that and evaluating it. So more to come at a later date. But now we know these reactions are happening. So let's take a look at how they impact formation properties, specifically porosity and permeability. So we've seen evidence in the literature that reactions can occur in a variety of different spatial distributions. So in some cases, you have reactions occurring uniformly on all grain surfaces, shown in red here. Sometimes reactions occur preferentially along certain flow paths, or in some cases, they occur only in small pores or only in large pores, or maybe there's a case where only some of the mineral surfaces are actually reactive. And so these different spatial distributions of reactions might have different impacts on permeability. The way we commonly estimate the evolution of permeability is using a continuum scale equation like the one shown here. The problem with these equations is that you get a single permeability for a given change in porosity. And so they're not able to reflect any non-uniform structural modifications that we have in our system. And so we need to account for changes at the pore scale. And we can do this with pore network modeling. So we can define a system of pores and some kind of lattice. We can use information on pore and throat size distribution and connectivity for the specific sample we're interested in. We can have a reactive fluid flowing through the system. We can solve for the pressure in each node. And then at the continuum scale, apply Darcy's law and get permeability. And so we've done this considering a variety of different spatial distributions of reactions in the network. We've looked at uniform reactions on all surfaces, randomly distributed reactions, which correspond to only a fraction of minerals being reactive, and then reactions that are size dependent, occurring only in small or large pores, or initiating in small and large pores. And then try to understand how porosity and permeability evolve, and then whether or not these empirical relationships are able to reflect those alterations. And so the work, this work was done by my undergrad researcher, Jacob Benziger. So here we're going to use the same sample that we talked about for reactive transport from the Paluxy Formation. We took some CT images of the sample and got information on their pore network structure from PN extract. So we can get pore and throat size distributions as well as connectivity. And then carried out a series of pore network modeling simulations. So here we have the simulation results for uniform reactions. We have a variety of sub-scenarios, which is each of these different colors. And for each sub-scenario, we carried out 1,000 pore network models and then have plotted the results. So the pore network model simulations using the unaltered pore and pore throat size distributions are shown in blue. And then we have dissolution scenarios and precipitation scenarios. If in this top plot, we have uniform reactions that alter pores and pore throats by some extent relative to their initial size. And on the bottom, the reactions occur as uniform thickness coatings on all pores and pore throats. So you can see in each of these scenarios, we have an increase in porosity and permeability with dissolution and a decrease in porosity and permeability with precipitation. The black lines on these plot are those most common or commonly used macroscopic porosity permeability equations. And so you'll notice for these uniform reaction scenarios, they're captured pretty well by the macroscopic porosity permeability equations. Now if we look at randomly distributed reactions, so this corresponds to only some of the minerals being reactive in our system. We can see something similar to the uniform reactions where we have increases in porosity and permeability with dissolution and decreases with precipitation that are reflected pretty well with the Verma-Pruth equation. Now, if we look at some of the size-dependent reactions, on the top here, if the reactions only occur in small pores and pore throats, you can see we get much more extensive changes in permeability with dissolution and precipitation, and that this is not captured as well with these macroscopic equations. If the reactions occur only in large pores and pore throats on the bottom, you have large increases or decreases in porosity with really little change in permeability, and this is also not reflected well by the porosity permeability equations. Now, if we consider a scenario where reactions initiate in small pores and pore throats, on the top, you have initial rapid changes in permeability and don't start seeing changes in porosity until you're impacting larger pores and pore throats. On the bottom, if the reactions initiate in the largest pores and pore throats first, you will see large changes in porosity with little change in permeability, and then start impacting permeability once reactions are impacting smaller pores and pore throats. And neither of these is captured by these macroscopic porosity permeability equations. But in red here, we have modified the Verma-Pruss equation, and we're able to find something that is a better reflection of the porosity permeability evolution for these systems. And so if we think about what's going to happen at the Biloxi formation once we inject CO2, this particular sample or formation has about 24% reactive minerals. So the star is the initial porosity and permeability. And so if we think some of those things are going to dissolve, we could have, large range and potential porosity permeability evolution. And it really depends on the spatial distribution of the reactions. And so sometimes those macroscopic porosity permeability equations work really well, but they're really limited in terms of reflecting permeability evolution for when reactions depend on pore and pore throat sizes. We've also explored the impact of different pore and pore throat size distributions on permeability evolution using a similar kind of approach. We found that qualitatively, that doesn't have a large impact on porosity permeability. We did observe, though, if you have few small pores and pore throats, you have less potential for clogging, and that overall those porosity permeability equations work better. This is also the work where we developed this modified Verma-Pruss equation for the size-dependent reaction scenarios. And then more recently, we've considered systems where you have simultaneous mineral dissolution and precipitation. This was done by my undergrad researcher, Molly Sabo. And so here we're having dissolution and precipitation occurring in the same network. These simulations we considered on the left here, dissolution at the inlet of the network, and then precipitation downstream towards the outlet. And what we see is that we have an increase in porosity, but a decrease in permeability, and that's not captured by the macroscopic porosity permeability equations. And then just as a kind of numerical experiment, we consider the opposite scenario where you have precipitation at the inlet and dissolution at the outlet, and you see the same evolution of porosity and permeability. And so when you have these discrete reaction zones within your network, this is going to result in porosity increasing and permeability decreasing as the fluid has to pass through some region where all of the pore throats have been constricted, which has reduced permeability. On the other hand, if reactions are randomly distributed throughout the network, so in some places the pores and pore throats are getting bigger, dissolving, and in other places they're getting smaller as precipitation happens, then you increase porosity, but you can maintain preferential flow paths and maintain the permeability of the system. So now I just want to share with you briefly what we've learned about geochemistry and energy storage systems. So we've mentioned that when you have excess energy from renewables, you can use that to inject a working gas into the formation. And then when you want to recover that energy, you can extract that gas. And so to initiate the system, thinking about storage in porous saline aquifers, we're going to inject a cushion gas. And so the cushion gas serves to increase the pressure of the formation to the operational pressure, but also push the brine away from the injection well. And so thinking about which gas you're going to pick for the cushion gas, you want something with a high viscosity ratio when you're comparing the viscosity of the gas versus the brine, so that it's more effective at pushing the brine away from the injection well. So these are, on the right here, plots of viscosity ratios for commonly stored gases. And you'll notice that CO2 is a really favorable choice of cushion gas. But from our investigations into geologic CO2 sequestration and saline formations, we know that CO2 is reactive. So will this reactivity inhibit our use of CO2 as a cushion gas in energy storage systems? So here we carried out some reactive transport simulations looking at the reactions that are happening in the acidified brine zone adjacent to the cushion gas boundary. So here you're going to have some different kinds of flow patterns where when you're injecting gas, you get flow away from the well, and then when you're extracting or recovering that energy, the flow reverses and goes back towards the well. And we considered a couple different simulations that I'm just going to show you the highlights from. The first, we're comparing the reactions with that occur for CO2 storage only, and that Porosity formation we've been talking about. And then we looked at the impact of different operational regimes. So if you're operating with continuous injection extraction versus cycling injection storage and extraction. And this was work that's done by my PhD student, Shadera. So here we have the simulation results and compared to CO2 storage. This simulation's for 120 days, looking at a 15 centimeter domain. If you're thinking about time here, so the initial condition is this dark green line and the solid lines, and then moving towards these dotted lines. So you can see relatively well here with smectite. And we're looking at some of the volume fractions, the most interesting ones I've put here. And so in injection-only systems, which is CO2 storage, you can see we have depletion of calcite across the domain. We have pretty extensive siderite dissolution, as well as smectite and muscovite. On the right here are the results for the injection extraction flow regime corresponding to energy storage. You can see we have some calcite dissolution closest to the boundary with the CO2, but then really no further dissolution further into the formation. We have really minimal siderite dissolution. We do have some smectite and muscovite dissolution across the domain, but overall the reactions are much more extensive in a CO2 sequestration system, where you're getting limitations in the extent of reactions here from flow cycling. Now, if we look at those different flow regimes, so considering injection extraction versus a system that operates with the storage period, so injection, storage, extraction. Again, the same domain, but now we're looking at over a 15-year time period. So the initial mineral volume fractions are the solid red line, and then kind of time moves downward here if you're looking at the siderite plot. So we have, as before, we have dissolution of calcite near the closest to the injection well or close to that CO2 plume. But then we also have some dissolution further away where you're mixing with the fresh brine. We see siderite and smectite dissolution throughout the domain. If you're comparing that with the system where you have storage, you'll notice that these plots look really similar. We have some slight variations in the extent of calcite dissolution, where you have slightly more dissolution when you have storage near the injection well and slightly less further into the formation. Comparing then porosity evolution across the domain. So the initial porosity here is about 25%. We can see near the injection well, you do get some pretty extensive increases in porosity up to about 35%. Also some increases further into the domain, but the majority of the domain here has much more limited increases in porosity. And so this suggests to us that that potentially we can use CO2 as a cushion gas, even though we know it is reactive. So the cyclic flow here is really going to limit the extent of reaction and therefore the extent of porosity increase that we're seeing in the system, which is really favorable for our energy storage operation. So with that, I would like to acknowledge support of funding for this work. These are some of the people who have done the work, my group that I've shared with you today. And shameless self-promotion, I'm looking for some additional PhD students if you know anybody who's looking. And thank you so much for your attention, and I'd be happy to take any of your questions.
Thank you very much, Lauren, for this extremely interesting and informative presentation and talk. I'm going to take your screen out, and if you can, browse your Chrome browser, see if you can see us.
Yes.
Because we are, okay, excellent. So we have already many questions posted. I bet myself and Kamal have also many, but we would rather give the floor first to the audience. So without taking any further time, Kamal, please start with the questions.
Thank you, Hadi, and thank you, Lauren, for this fantastic talk. I learned a few things.
Yes,
again,
me too as well. These reactivities are quite complex, but very fascinating.
Yeah.
Like I already said, I've got a couple of questions, but again, I'll reserve it like the later stage if we have some time. So we got a range of questions from going from different scales, modeling, rel pumps. So I'll go one by one and I'll try to group them if I can. But I'll start with the first from Leila Hashmi, who's saying, thank you for the very interesting presentation. How can we scale up the reaction rates in the lab to the field to conditions? Given because we got heterogeneity there, uncertainties are there. So any thoughts on this?
Yeah, so that's something we're really working on with our accessible surface area investigation. So thinking about the way we're modeling reaction rates at the continuum scale or larger scale, we usually use that transition state theory rate law. And so, I mean, that's great because we can easily include that in our large scale simulations. But really the largest source of uncertainty then is what do you put as that surface area value? And so our work so far has shown us that potentially accessible surface area is a better approximation than some of the more simplified approaches that we've been using so far. And so what we hope is that this can improve simulations at the larger scales using an accessible surface area value, at least compared to the variations we get using geometric surface area or specific surface area. And so that looks promising so far.
Sounds good. Thank you. Jumping really towards the last question first. It's Kiarash is asking, many thanks. Do you also investigate how would the fluid temperature affect the precipitation or dissolution rate?
Sure. We haven't investigated that explicitly, but if you have higher temperatures, you should have increased reaction rates.
Fantastic.
So then, I'm sorry, Kamal, then in scaling up to the in situ conditions, then given the temperature, we could also consider that scaling up the reactivities. Yeah. Mm-hmm. Okay, just to make sure.
Sure. And we got a couple of questions on modeling work. So there's a one from Pu Wai Huang. Thanking you for this interesting presentation. What kind of reaction models have you used in the pore network modeling of the porosity permeability relationship studies? Is it involved with some multiple species?
So in the pore network modeling work here, to keep the applicability for any kind of reaction, we're really just making actual physical changes to the network. So we're assuming that there's some kind of reaction happening that's going to change the pores and pore throats in a specific fashion. And so we don't have a specific reaction system that we are including in that work, but just considering if you had a scenario with different physical all types of reactions, you can collect several of those from literature and different applications. But to keep it as general as possible, we don't have one specific set of reactions that we had considered.
Okay. Thank you, Lauren. There's a question from Ahmed Hussain. I think I understand half of it, but maybe it's my limited knowledge in that. do you use mineral surface area of a mineral to model its precipitation rate? And if so, what do you use to model the precipitation rate if the solution has no mineral or no surface area initially?
So that's a great question. And so everything that I've talked about today with at least when we were modeling specific reactions, and the accessible surface areas, that really only applies to dissolution. And precipitation is a whole nother challenge that we're, I don't really have anything specific to share with you yet about it, but it is definitely another challenge, because you also have to account for nucleation, right? And there's the activation energy barrier you have to overcome. And so whatever we've done so far has not focused so much on simulating precipitation, which is very challenging, but in improving the simulations of dissolution. And so our pore network models, again, with precipitation, we've assumed that there's just those physical changes happening in the network, and what happens to permeability there. But yet for reactive transport right now, with permeability or with precipitation, yeah, you put in some surface area value, and that's kind of where we are. So there's a lot of, I think, outstanding questions and room for new knowledge in that area to improve those simulations.
Thank you. There's a question from Wilhelm van Hoyer. Okay, I'm sorry, my apologies. I'll read his question, then there are 3 questions from Johan. I'll go for that. And she's saying, thank you for this informative talk. How different are the reactivities involved in CO2 storage compared to with the very topical issue of hydrogen storage? Would hydrogen be as reactive as CO2? Can you please comment on that?
Sure. And so I think that's also something that we as a community, right, are trying to understand. So different kinds of reactions are going to happen in hydrogen storage. So the redox reactions are going to be more important. Also, potential microbial reactions can be very important. We don't really have a great understanding of what kinds of reactions might happen in hydrogen storage systems. I think it's really an open slate. We know hydrogen is potentially less reactive than CO2, but I think there's a lot of unanswered questions and opportunities for new knowledge growth in that area.
Yeah, sure. Thank you. There's a few questions from Johan. He's saying, thank you for the great talk. Have you considered about how would this reaction affect relative permeability, for example, because we are talking about CO2 brine system in that case?
No, I haven't considered it yet. That is even more complicated and a great question. Yeah, so we've been looking predominantly at the CO or the brine saturated region. So where you're going to have CO2 can be desaturation in the brine, but what's going to happen in the multi-phase region where you have CO2 and brine could be potentially even more complex. And we haven't considered it yet, but it's definitely a good question, and I don't really have any good answers for you yet.
Yeah, indeed, it's a bit complicated in this sense. Yeah. Thank you, Lauren, for that. So I've got a couple of questions very similar from Yuang. I'll go for both of them together. So, were the images of experiment they were done or performed in 2 dimensions, or how would they correspond to 3D rocks? I think the next one is also similar to, I assume, microscale fluid dynamics would be more complex than 3D. Can we do microcity based imaging of reactions involved? Would it be possible? Like, let's say we got resolution or not. This sort of things are there already.
Yeah, so there's been a lot of advancements in resolution of CT imaging. And so something we're working on now is tracking 3-dimensional evolutions of pore structures at micron scale with CT imaging. You can get some different kinds of information. So you get information about the 3D pore structure evolution, but you can't get information on what specific mineral phases are doing because we can't identify minerals reliably with CT imaging. So ICM imaging is only 2 dimensions, but you can figure out what the minerals are and look at them explicitly. With the CT image, you can only distinguish some phases, and it depends on your sample. So I think that ideally we'd be able to see everything, but we can't. So they really have to be complementary to each other.
Sure. Thank you for that. Can I throw my question inside, because I think it's slightly related to that. When you consider the accessibility, are you also considering the flow fields in 3 dimensions in that case? Because would it depend on the flow field where the flow is going, then do you have more reaction in that case?
Right. So for quantifying accessible surface areas, we do account for 3D pore connectivity. So we use CT imaging to quantify the connected surface area in the 3D pore network. Our simulations were done at the continuum scale, so we're not resolving pores then, but really helpful for understanding upscaling, like the question earlier, because we're just saying you have some porosity, right, and there's some flow, and then this is the amount of mineral. So that's not done at the pore scale, but very helpful for the upscaling application.
Sure, thank you.
Mm-hmm.
Thank you for asking, answering two questions altogether.
Sure.
There's a question from Sarah Bahani. Again, thank you for the great talk. Question is about new equation for estimating permeability. What ranges of temperature, pressure are they applicable to?
So when we were looking at the size-dependent reaction scenarios, again, we've just assumed that we have some kind of physical changes in the network. So, as long as you have that kind of similar alteration or reaction pattern happening in your network, I don't think that there's a dependence on temperature or necessarily on pressure.
Okay, thank you. There's a question from Tuafik. Sorry about that. My my skills in reading the names are not good. Tuafik Nassan, thanking for the valuable presentation. What was the state of CO2 used in your experiments? Was it liquid, supercritical, or gas? And did you study the effect of water on the process, like intermittent injection, if you've done that?
Sure. So the simulations do assume you have a supercritical CO2, and then we're looking at the brine saturated region. So we've accounted for, what is the phase equilibrium between the CO2 phase and the brine, and then have done the simulations considering CO2 saturated brine under the certain temperature and pressure conditions. I think most of the stuff I talked about today were all simulations. So yeah.
Sure. Thank you. There's another question from Karash. It's regarding the modeling part. Do you consider reactions or equilibrium or kinetics? Do you consider that?
So the mineral dissolution reactions are all kinetics.
Okay. Thank you. I don't see any further questions there, and I've already asked my question, which I was about.
This is the first talk we have answered quite so many and so precisely that we have. I think you have Lauren. You answered maybe 15 questions in about 20 minutes. It's like we have this kind of shows with competition shows with so many questions asking from the parties. But thanks very much for being so precise and so to the point. I think if Kamal, you ask me, you allow me to interrupt a bit also to, Lauren, you studied also cyclic injection production, and that becomes very relevant for cyclic energy storage. And now having different cushion gases for, let's say, hydrogen. Now, one of the topics is maybe we can use CO2 as cushion gas for that purpose or other things. Now, if we have other gases in this cyclic injection production, would you be still less concerned of the reactivities and purity loss potentially?
So I think that CO2 we know is very reactive. Some of the other things that are being looked at for cushion gases is just air, nitrogen. You probably, especially with hydrogen storage, you need some kind of cushion gas because it's just going to flow away from your well otherwise. CO2 I think is going to be the most effective choice because of that viscosity ratio with brine. You have some different kinds of reactions happening. Like if you use air and there, I think that the redox reactions are going to be important as well. And how reactive that is compared to CO2 probably depends on what kind of minerals are in the formation that you're looking at. So in some cases, maybe you don't really have a lot of reaction at all. So I think it just depends on what the composition of the formation is and what the choice of cushion gas is. So like if you are going to use air, but you don't really have anything that's redox sensitive, maybe you don't really see any reactions happening. Just like with CO2, if you have a formation that, if you don't have any carbonate minerals, you'll have things, much lower extents of reaction if you use CO2 as the cushion gas. So it is definitely formation dependent as well as whatever your choice of cushion gases.
So it would be quite meaningful to get the real sample of the formation for a study of the feasibility and especially also the brine from the reservoir, if we can get it, especially with microbial activities, what type of microbes could be there, as you said as well.
Yes, definitely.
Makes it quite complicated. It is a complicated system, and now adds even more to this kind of bio system that you have life cycle for them to be active in the lab, especially.
Yeah, and I think we often also think that like, all reactions are going to be bad for our operational of the system, but that's maybe not necessarily true, right? So if you have some amount of dissolution that can increase your storage capacity, but that could also mean that maybe you're increasing permeability, and so then your gas is going to, you could inject it easier, but then it might also flow into the formation easier, and so you have to replenish it more. But the same thing is like if you're having then precipitation, depending on where that is, that could clog up your formation, which might lead to challenges in operation if you're, challenges more likely to potentially overpressurize. But maybe it could be good because you're kind of just trapping all of your gas closer to the well, and that will actually increase the operational efficiency. So I think it's slightly more complicated than.
And as my last question, I wanted to ask your comment and advice on what would be the right scale and approach to characterize or quantify this kind of reactivities for CO2, for other gases as well. You mentioned about CT that would not allow us really take minerals, or even core flooding. I have seen colleagues do core flooding for reactivity and just, flooding with some sort of reservoir brine for geothermal systems even, and see how would be the permeability in the core sample changing, and then getting permeability, as you can measure their permeability, and that's what you can measure somehow. And then at the very small scale of SEM images, you can really look at the minerals that precisely. What would be your ideal work to identify this and resolve this challenge?
That's a very complicated question. I think that you kind of have to go across scales, honestly, and it probably depends on your formation. So, some formations that have really intricate things happening at small scales, it might be important to account for those, but that's not necessarily every formation. And it depends on what specific minerals are present and how they're distributed. So for me personally, I think, I want to know something about what's happening at the pore scale and what that looks like. Other people you could talk to and say, we really need to understand the molecular scale. And I'm kind of jumping over that scale. And so I think it kind of depends on your perspective. So most of our work is kind of in this pore to core scale, or this like micro continuum scale. And so that is my personal perspective, because pore scale reactions impact permeability. But you could also, if you zoom out even further, then you have larger field scale things happening, right, with lenses, and that's also not things that we're necessarily considering. So I don't think there's like a yes and no kind of answer for the scale
it's like many other things, but it's a very, very important and impactful thing, because it's very, as you said, for hydrogen, especially other gases that we would like to work on, it's a little bit of still an unanswered question. And I want to take the most possible chance of having you here. Imagine I do the core flooding with this reactive thing, and then is it possible or meaningful to get some sort of cut of this after the system at that core scale has been flooded, and now I observe the system behavior in the core scale, and now then I take some sort of cuts through it and do SEM afterwards. Would I damage the rock by doing that? Would you do that? If I do that, you would think that it would be a kind of foolish thing to,
No, actually, we're doing that right now. So you look for our paper. It needs to be submitted soon. Actually, with all the sandstone samples that we analyze, this whole slew of data, now we're reacting them all and tracking their pore structure evolution with CT, and then are going to do all of the accessible surface area analysis afterwards to try to understand how the surfaces are reacting in like acidic reaction conditions. So no, not foolish. We do that. We're working on that.
That's great.
Hopefully submitting soon. But yeah, it's true that maybe you can, have some artificial changes, but you can, if you're doing your CT imaging while your sample is in the core holder, right, you can see what that looked like. And if you kind of compare that with what it looks like in your SEM images, maybe
No,
get an
I would
idea.
fully agree with you, because you may just change maybe the roughness, etc., but you
Right.
wouldn't really cut the mineral. I mean, this
Right.
is absolutely, no, that would be quite meaningful. I fully agree.
Yeah.
So we could end up till
I've got-
midnight. Kamal, one question, please.
I'll
She has other things to
ask
do.
only one. Just for information for maybe for myself or other audience, you showed pore network models. Do you develop these models, or do you use people like from open source available somewhere? So if someone wants to use it.
So I know that there are several open source pore network models. The one that we have, we just programmed in MATLAB. But yeah, we haven't used any of the open source ones yet, but I know there are several out there. Yeah.
And are you considering to make it open source yourself, like your program?
Oh, I have. That's a good question. I haven't. I honestly haven't thought about it. No, nobody's asked me for it, so I don't know if anybody wants. Like, there are so many of them, but yeah. If you're interested, let me know.
Yeah, and I think I've seen some questions regarding the pore network modeling, and then I thought maybe if somebody wants to use a compare model, I think it would be fantastic.
Oh, sure.
Different people putting online. Yeah. Well, thank you,
Mm-hmm.
thank you, Lauren, for all the discussion. Fantastic discussion, answering all these things. I'll give back to Hardy now.
Thanks a lot for all the wise words, and I did learn a lot. And thanks very much for being so bearing with our questions and tolerating us with all these questions that we ask, especially also to the audience as well. I like to also take the last minute chance to introduce our next week speaker. Next week we will host Helen Robinson from University of Glasgow. Helen will speak about linking geological structures and hydrogeochemistry to identify potential impacts of geothermal resource development in Kenya. So quite an interesting talk. Again, geochemistry, it's becoming, I personally think, I do more fluid dynamics, but I personally think geochemistry will be very, very, even more important than what it is today. So until next week, the same time, 4 p.m. Central European, 3 British time, 7 California, wherever you are and watching even later this talk. Stay happy, healthy, and then tuned in next week to the same channel for another geoscience and geoenergy webinar. Thank you, Lauren. We did learn a lot, and that was really nice. Thanks a lot.
Thank you.
Thank you. Have a nice day. Bye-bye.
Bye.
Bye.